Yes, we can hear.
And are slides visible?
Yeah.
Okay. Okay, so yes, so first we will be discussing in roofline model and arithmetic intensity. So here we have first question. So here we have the graph between attainable flops and arithmetic intensity. So yes, so they are asking that which of the following optimization if we do, we will get, we will move in this direction, we will benefit in this direction they are asking. So we have three options. First one is access data from L1 cache instead of main memory, NUMA hour allocation, and vectorization. Oh, so yes. So first, yes. So this graph is in logarithmic scale. So optimizing here means before the reach point. Before the reach point, it is memory bound region, and after reach point, we have computation bound region. So here, this optimization means that we are increasing the memory bandwidth. So to increase the bandwidth, yes, if we access data from L1 instead of main memory, we have much better bandwidth. And also if allocation is done according to where requirement is there, NUMA aware. If you do memory allocation accordingly, then we will get better memory bandwidth. So yes, so A and B we get in this direction. If we do vectorization, the memory bandwidth will be the same, but the computation will be much better. So that is actually optimization in this computation bound region. So vectorization won't help us optimizing in this direction. So answer is A and B. Then next we have to find AI of these loops. So here we have three loops and we need to find AI. AI is arithmetic intensity, that is number of computations done per byte fetched from the memory. So in these loops we will assume that X is stored in register, so we won't fetch it from memory. So as you can see that in the first loop there is only one computation in each round, and in each round there are 8 bytes fetched. We will assume that it is one word is of 8 bytes. So 8 bytes are fetched. And in second one we have two computation, that is first we have multiplying and then we are adding, so two computations. And similarly in the third loop we have three computations and the same 8, in each one 8 bytes are only fetched. So we have number of flops is 1 2 and 3, and so and data fetched is 8 bytes. So AI is 1 by 8, 2 by 8, 3 by 8 for these three loops, one computation per 8 bytes. Now we will find AI of these codes. So first code we have is of vector addition, that is x of I is equal to x of I plus y of I. So in each iteration we will first fetch x of I and then we will fetch y of I. We will add them and then we will again store it in x of I. So actually there is the x of I is repeated here, but we will anyway we have to do two memory access, one for reading x of I and one for writing x of I. So we have to count it twice. So total 16 bytes we are fetching and 8 bytes we are storing, so total 24 bytes memory access we are doing. And total computation which we are doing is only addition, only one computation. So one computation per 24 bytes, three memory access, one computation per 24 bytes. Then second we have next code 2, that is ax plus y format. So here also the same thing, we are fetching x and y and we are doing ax plus y and we are storing back it in x of I. So again memory fetched will be 3 into 8 units, and the number of computations will be here two computations because we are multiplying a and x and then we are adding it with y. So two computation per 24 bytes. And the next one, last one, is the inner product. So in vector inner product we are taking. So here again we are fetching x of I and y of I. The s is stored in register, so totally we are fetching 2 into 8 bytes, and then we are doing two computations, one multiplication and one addition. So we have two computation per 2 into 8 bytes. So this is how AI we are calculating. Now we have to find AI for these two codes. These two codes are functionally similar, but they will have different AI. So here we can see that we have separate for loops for both the computation. So we will first calculate the AI for the separate loops. So for the first loop, we are doing one computation in each iteration, and in each iteration we are fetching 8 bytes. So AI is 1 by 8. And similarly for the second loop, we are fetching 8 bytes and we are doing two computations. So we have AI is equal to 2 by 8 bytes. And for the code one, the total AI if you see, so we are fetching AI two times. So we are totally fetching 16 bytes and we are totally doing three computations. So AI is 3 by 16 bytes. But in code 2, we will fetch AI only once. We won't fetch AI twice. We will have the AI. So actually in code 1, after iterating, the cache is not able to hold. So that AI will be lost. So we won't have that AI in cache. But here, since we are doing it in the same iteration, we will have it with us. So we'll be fetching AI only once and we'll doing three computations. So AI is 3 by 8. So this has much better AI. Yes, this one also is similar. Here also we have this two separate loops and here we have one single loop. So in the first loop we are doing one computation in each iteration and we are fetching 8 bytes. And in here second loop actually we are not having any floating point operation. We are just fetching it and then we are comparison does not require floating architecture hardware. So second loop has no. Yeah, we don't talk about AI in second loop. So total here we will be doing total n computations, but we will fetch this one also and here also we will be fetching. So total memory access will be 2 into n, 2 into n words. And in second code we will be fetching only one time each one. So total n words we will be fetching and we will be doing total n operation. So the for first code the AI will be 1 by 2 operations per word and for the second code we will be having one operation per word. So second code has better AI. Okay, so now we have next question we'll be discussing. A computer has memory bandwidth of 2 gigahertz per second and peak performance of 8 gigaflop per second. So we need to find its AI. So how do we find the AI? We have to find the AI at rich point. So at rich point, AI into the bandwidth will give us the peak bandwidth. So here we peak performance. So here peak performance we have 8 gigaflops per second and memory bandwidth is 2 gigahertz per second. So AI is peak performance divided by memory bandwidth. So we have 4 flops per word AI at rich point. Now here we have a code stencil computation code that is operating on n by n array. So we have to find its AI. Okay. So as you can see in the code, we are taking n minus 2 square elements, reading it and writing it. Actually, reading will be having 4 into n minus 2 elements more, but we can ignore that. It is much smaller when compared to n minus 2 square. So total operations, if you see, in each iteration we are doing 1, 2, 3, 4. 4 multiplications. No, sorry. 1, 2. 2 multiplications. 2 multiplications and 4 additions. So, and there are total n minus 2 square iterations. So total 6 into n minus 2 square computations we are doing and each one we are reading and writing back. So 2 into n minus 2 square memory words we are accessing. So AI is 3 flops per word. AI at rich point for this device was 4 flops forward. Okay, and for this program we are getting AI is 3 flops forward. So this program is in memory bound region. So the runtime, the speed with which program runs depends on the memory bandwidth. It is in memory bound region. Now suppose if peak performance is quadrupled and the effective memory bandwidth is doubled, then what is the case they are asking? So if peak performance is quadrupled, so we have peak performance of 8 gigaflops per second, that is quadruple, now 32 gigaflops per second, and memory bandwidth is 4 gigawatts per second. So then A at reach point we will have 32 by 4, that is 8 flops per word. So now 3 is again smaller than 8 only. So it is, so the code is still in memory bound region. Now we will see next question. So here we have a 3 gigahertz processor which can execute 4 floating point operations in each cycle. Okay. So 4 floating point operations in each second. So first we will calculate how many floating point operation it can do in each second. So it is 3 gigahertz processor means in each second it is covering 3 gigacycles. So 4 into 3, 12 gigaflops per second it will be able to do. And it has peak memory bandwidth of 10.6 gigabytes per second. Okay. And they have given a kernel to us and they are asking what percentage of peak performance would we expect the kernel to obtain. Okay. So yes, so in 1 nanosecond the processor does 3 cycles. So in each cycle takes 1 by 3 nanoseconds. So it does 4 floating point operation in each cycle. So it does 12 floating point operation in each nanosecond. So it does 12 gigaflop operations in each second. So this is our peak performance and memory bandwidth is 10.6. So A at reach point is 1.13. Now we will calculate the AI for the code. So in this code we have total 1, 2, 2 floating point operations. We are fetching 3 words and writing 1 word. So we have total 4 words memory access and we have 2 floating point operations. So AI will be, so AI is 2 operations per 4 words. So that is 2 by 4 into 8 flops per byte. 1 by 16 flops per byte. And AI of the AI at reach point was 1.13. So as 1 by 16 is much smaller than 1.13, the kernel is in memory bound region. So in memory bound region, the performance is AI into bandwidth. So AI is 1 by 16 and bandwidth is 10.6 gigabytes per second. So that is 0.6625 gigaflops per second. And so they are asking percentage of peak performance that it obtains. So that is 0.6625 gigaflops per second divided by peak performance, that is 12 gigaflops per second. So that will come out to be 5.5 percentage. Okay, we are having a doubt here. The array accessed can be anything from int to double, which changes the number of bits fetched per load. Doesn't AI change according to that? Yes, AI will change according to that. Here we are assuming that each word fetched is of 8 bytes. Each array element is of 8 bytes. We have assumed that in this tutorial. Okay. Okay. So next we will see tutorial on floating point numbers. Are the slides visible? Hello? Hello?
Yes, yes.
Okay. Okay. So yes, floating point numbers we are seeing. So here we have a code with us. So yes, they are asking what will this code print. Okay. So first they are storing 1000.43 in a float A and 1000.0 in float B, and they are printing A minus B. Okay. So here actually what happens is 1000.43. This is actually not representable exactly in binary number, infinite with finite number of bits in binary. So the computer actually stores an approximation of that. So that will actually comes to, so the actually it will store 1000.429993. The binary representation will approximately be equal to this one. So the difference A minus B will return this number, and it won't return 0.43 exactly. Okay. And now they're asking what if you change it from float to double. So yes, so if you change it from float to double, the 1000.43, it is still not exactly representable in binary number. But since double has yeah, more digits for its decimal part, it will be able to represent it more accurately, better than the float. And since the cout prints only up to 5 to 6 decimal digits, so the nearest number which we in the sixth up to 6 decimal digit, the nearest number will be 0.43. So when they both are stored in double, the difference will exactly be printed 0.43. Okay. Now here we have two numbers 23.42. Once it is stored in float, and in the second line it is stored in a double queue. And now they are assigning a boolean variable is equal to the result of evaluation of p is equal to q. Okay. So yes, so here what happens is 23.42. Again, this is not exactly representable in binary. Okay. So the the computer will represent it with the nearest approximation which it can represent. Okay. So the float approximation will be weaker than the double approximation. Double will approximate it much better since it has more storage. Okay. So when we do p is equal to q, the float will be typecasted to double, but the float won't be 23.42. The float stored in p won't be 23.42. It will be the some approximate of 23.42, right? That will be typecasted to double. Okay. So that won't be the same as the 23.42 stored directly in double. Okay. 23.42 stored directly in double will give the best approximate which can be stored in double. But when you store it in float and then you typecast it to double, it will be the approximate which can be stored in float. Okay. So the result of p is equal to q will actually be 0. It won't be 1. Okay. Now we have another code. Here we are storing float p is equal to 64 and double q is equal to 64. Okay. So here again we have the same question. P is equal to q. So what will be this print? Okay. Now here 64 is exactly representable in binary, and it is a small number which can be represented by both these data types, right? So and then when doing p is equal to q, the float will be typecasted to double. So since both are stored exactly, the double representation will be the same for p and q. Okay. So here we will get actually 1. Okay. So yes, this is what written here. 23.42 is not stored exactly, and 64 is stored exactly. Okay. Okay, now here we have another question. We are having float x is equal to 0.1. Okay, and here we have two conditions. If x is equal to 0.1, then printf if, else if x is equal to 0.1 f, printf else if, else printf else. Okay, so here again the 0.1 is not exactly representable in binary, so its approximate will be stored. So in C++, if you write a floating point number without any qualifier, it is taken as a double number. Okay, so inside the if condition we have x is equal to 0.1. So the right hand side 0.1 is taken as double, and so x will also be typecasted to double. Okay, so but x is actually not 0.1, it is the floating point representation nearest approximate in which can be stored as floating point. So that one typecasted to double, it won't be same as the 0.1's double representation, right? So we won't get that. And next, in else if we have 0.1 f. This f is actually qualifier which tells the C++ compiler that this 0.1 you have to treat it as a floating point number. Okay. So here the right hand side is also the floating point representation of 0.1, and the left hand side is also floating point representation of 0.1. So we will get else if printed. Okay. So again similar type. Here we have printf, and we are printing size of x, size of 0.1, size of 0.1 f. Okay. So x is floating point number. So floating point number takes 4 bytes. Size of 0.1. 0.1 without any qualifier is treated as double. So we get 8 bytes. And 0.1 f. The f qualifier will make it float. Okay. 0.1 is not exactly represented by float. Okay. Now I have some code with me, C++ codes that will demonstrate.
Before we go ahead, anyone has any questions on this? And actually, Gaurav, you can, when you do that code style, you can, I think that if you have you uploaded those codes on Teams?
Yeah. Yes, sir. I have uploaded the codes on Team.
Okay, so the next part is where we have several C or C++ codes. You can see them in the Teams, and you can download them. You can run them. You can see the output yourself. And Gaurav, you can do that in like a question answer style. You can ask students to reply instead of explaining everything yourself.
Okay. Okay,
and,
sir.
They can, maybe you can share your screen where you run them on that, where you run those C++ codes, but don't immediately tell what is the answer. Let them think or let them
Okay, sir.
speak.
Yes, sir. Hello. Yes, the codes are uploaded in the file section in Teams. You can download them and you can run it parallelly, or you can run and you can think and you can tell what will be the output of each of them. There's a tutorial sheet also with that. I have uploaded that. You can see the questions in that. I will be discussing that. Okay.
Excuse me, where you put those things in Teams?
Yes, in Teams there is file section, right? In the top, in the file section, week 1, day 3, there
Okay,
is
okay, okay,
floating point folder. In that it's there.
okay.
You can download it. I will. Okay, shall I start? Naman is saying something I can't hear.
Actually, that whatever you have uploaded, that is hidden.
Hidden.
Uh,
How can it be hidden? If it is hidden, then how can you see it?
I cannot see na. That's why. Can you put in conversation kind of thing in week 1, day 3?
Can you try to use the link I have sent on the chat?
Okay, then I will.
It is a link to the same file, but I have given a link just in case you cannot access it through the folder.
Okay, so shall I start?
Excuse me, sir. Still, I don't have those files.
You're not able to access it from the link also?
Yes, sir. Sir, can you post it like those files in the conversation? Because that week 1 day 3 is hidden channel, I think. That is showing to me.
Then, sir, can
It's
you?
not a channel. You can just go to files in the team and you can access it from there. You don't. It's not a channel.
Yeah, sir. I am in files, but there is no file to download.
Yeah, hello. I think you're checking in the hidden channels. It's in the general. So go to general and then check the files there. There is a folder called week. Like every week there is a folder. You can check it there. It's not there. It's in the general.
Okay. I thought you have sent it there. I got it then. Yeah,
Yes,
I
okay.
saw.
In the hidden channel. Okay, the name or sim. No, the folder name is week 1 day 3. It's in general channel only.
Now I got it. There was some confusion with that.
Yes, slides I will upload it later. Okay, so is my screen visible? Hello? Someone please type if it is visible or not visible. Okay. Okay. Okay, so first we have find delta. We have this program with us and we need to find its output. Okay. So here in this program we are having numeric limits function. Numeric limits is actually from in STL we have numeric limits that will give us the numeric limits. Minimum will give the minimum number in the data type and maximum will give the maximum number in that data type. Okay, so here in this code, this is simple code. Here we are seeing the limits of each of the data types. Okay, and for float and doubles, it will show the minimum possible representable number in the positive side only. Okay, because in the negative side also it is similar, we know that. So it will show the minimum possible number, the positive side, normal number. Okay. So yes, so here we can see this output. Here for character we are doing static cast to int, we are converting it to int the limit. Okay, So character is 1 byte, so it is limit is minus 128 to 127, 256. Similarly, short is 2 bytes, so its limit will be 2 to the power 6, 15 minus 1. Okay, and unsigned short is the same thing. We don't have negative numbers here, so all the bits are used to represent the positive number. Okay, and similarly, int and long, unsigned long. Okay, here we have float, double, and long double. Okay, so this float is the C++ float is IEEE single precision numbers. Okay, so in that the minimum number, smallest number, that is 1.17. That the smallest and the largest number is shown here. This E plus 0.038 is that 10 to the power 38. Okay, like that, 10 to the power 308, 10 to the power 4932. Double is IEEE double precision number, and long double is IEEE quadruple precision numbers. Okay. This thing sir would have thought how to calculate the smallest and the biggest number in the IEEE representations. Okay. That is the same thing. Here we are printing it from the standards. Okay. So that this is the first program, and that is the output. The program is entirely this. All the lines are same actually. We are printing the numeric limits minimum and numeric limits maximum for each data type. Okay. Okay. So here the second question we have double and int. Okay. So yes, here we have int 64 number, and then we are converting the to double the n and n minus 1, and we are comparing it. Okay, so whether they are equal or not, you have to say whether this will print 1 or 0. Means n and n minus 1 share the same representation or different representation. What does it print? Yes, you can type the answers in chat box. What do you think? Same. Okay. Yes. Yes. N and n minus 1 will share the same representation. That is the correct answer. Same double representation. Okay. So here actually we have this number. This is a big number. This number is actually greater than 2 power 53 plus 1. Okay. So yes, in double we have only 52 bits for fraction, right? So if you have any number that has more than 52 bytes, means excluding the leading zeros. Okay, if it is having more than 52 bytes, right? So then we can't represent it in the double form exactly, okay? Because we need 52, because only 52 bytes are there for fractional part, yes. So any other bit after the first 53 bits will be ignored, or it will be an approximate, right? We can make it 0. We will make everything 0 after the first 53 bytes, right? So only that numbers can be stored in double. So this number being much greater than 2 power 53 plus 1, the n and n minus 1 both will have the same representation. Okay. Okay. So yes, as we see in this question, like these numbers are not the big numbers we can't represent exactly in double. Okay? They are stored approximately only. But small numbers, they are exactly representable in double. So till which number are they exactly representable in double? Okay, we need to find that. So in next question we are having, next question is one about that only. So first number that differs, we have to find that the first number which differs from the exact representation and their double representation. Which is the first number that differs? Okay, differs from long. Change it to long. Double 8 bytes and long also is 8 bytes. Okay. So you guys think and type in the chat box. What do you think? Which is the first number which will differ? Okay. Think about smaller numbers, how they are represented in the floating form. Think of that. You will get it. Two power 53 minus 1. Okay. Naman, I think you are slightly missing the answer. Two power 54 minus 1. No, I'm not asking the output of the code given. I am asking any number not particularly of 2 power n minus 1 format. So normal long number, which is the smallest long number which can't be represented exactly in double. It need not be in 2 power n minus 1 format. Okay. What is exact question? Okay, so the exact question is, we have long numbers, right? So long numbers, when we can convert it to double, right? So small numbers like 1, 2, 3, 4 and all, if we convert it to double, we will have the exact same number in double. Okay, but after a certain number, its double representation won't be the same as the long representation. I mean, the double number won't be exactly equal to that number. Okay, so what is the smallest number where this occurs? I'm asking. What is the smallest number for which the double representation is not accurate? Did you get my question, Naman?
Yes, sir.
Hello? Did someone say something? Okay. So first, okay, because double is 8 bytes, so it could be 2 power 64. After that, it will not be equal to long. Okay, double is 8 bytes, but in double, we don't use all the bits to store the number. Like in double, store it in, we reserve 11 bits for exponent, 52 bits for fraction, and 1 bit for sign bit, right? So till 2 power 64, not all numbers will be still there. Yes, Sanjana Jain has the correct answer, 2 power 53 plus 1. Okay, not all numbers till 2 power 64 we can represent in double. In long we can represent. Long has 64 bits and 1 bit is for sign. So till 2 power 63 minus 1 we can represent it in long. Long. Okay. But in double we won't be able to represent that. Okay. So we will see why. Okay. Yes, Sanjana's answer is correct. So yes, so we will see first how those numbers are represented in double. Like if we have 1, how is 1 represented in double? So the fractional part for 1, This we will take 1.000052 times 0 and into 2 to the power 0. Exponent we have 11 bits for exponent we have. Okay. So 11 bits for exponent means we can do up to 2 power 10. So that is very big for us. So that is not, exponent won't be a limiting factor. Only the bits allocated for fractional part will be the limiting factor here. Okay. So suppose we have number like 11001. Okay, this is long number. Okay. Now how will this be represented in double? So this will be represented in double like this: 1.101010 into 2 power number 1, 2, 3, 4, 5, 6 bits. Okay. So 2 into 2 power 6. So 6 you can store it in exponent part. Exponent has 11 bits, so 6 can be easily stored. Like that, even for some big numbers, we can store the exponent part easily. We can just put a decimal point after the first one and then into 2 to the power that many thing. Okay. But when we have 52 zeros here, okay, when we have 52 zeros here, okay, when we have 52 zeros, this is 2 power. Assume here we are having 52 zeros, so this number is 2 power 53. No, this number is 2 power 52. Okay. And this number also we can exactly represent. We will just put a decimal point here, and there are 52 decimal digits. So into 2 power 52. Okay. Now the problem comes when we have 53 zeros here. Okay. If we have 53 zeros also, we don't have an issue. We can just put a decimal here, and the leading zero we can the last zero, trailing zero we can remove, and we can put 2 power 53. But when the last trailing zero, we make it 1, the next number after that number. Okay. This number we won't be able to represent it in double. Okay, because in double we have only 52 bits for the fractional part. Okay. But here we have 53 numbers. Okay. So we wouldn't be able to represent this number without the decimal thing. This number, that is 2 power 53 plus 1. Did you get it? Naman, did you understand?
Yeah, understood, sir.
Okay. Yes. So till 2 power 53, all the long numbers we can also represent it in double exactly. But after 2 power 53 plus 1, it will make approximates. Okay. Okay. So here this question in first number that differs in this program. Actually, this is in this program what we are doing is we are taking 2 power n minus 1 type numbers. Okay, 2 power n minus 1 type numbers, and we are iterating over that to find out in which number we are getting the difference. Okay. So here we are repeatedly running this loop. In this first, we have two strings, character array strings, ds and tsc. Okay. In ds we are storing the C version of the double, that is normal IEEE double precision format. Okay. We will store that in ds. Okay. And bc is a tool, some third party tool that will allow us to store with full precision. Okay. That has arbitrary precision. It can store in full precision. So we are storing both this format. This is the C format we are storing in original string, and using BC we are storing with full precision in another string TST. Okay. And then we are comparing it. Okay. And if the comparison is true, if both are same, then we will check the next 2 power n minus 1 number. Okay. If they are true, we will go for the next number. If they are true, we will print where we got the failure and we will break it. Okay. If it is true, we will go to the next number. So output you will get like this for up to till to the 2 to the power 53 minus 1. Both representation will be the same. Okay. In 2 power 54 minus 1, which is greater than 2 power 53 plus 1. There we will get the difference. Okay. This, see, here it is storing 2 power 54 only, it is storing, because the last bit it can't store. 2 power 54 it is storing. 2 power 53 it's not storing. 2 power 54 minus 1 it is not storing. The BC is storing exact number, the 2 power 54 minus 1, which we are expecting. Okay, but actually we the C format in C++ we are getting 2 power 54 for that number. Okay. Okay, next question, we have this program. Okay. So yes, here we have stored the same number 1 by 81. Here we are storing it in float, and here we are storing it in double. Okay, and here we are having a simple for loop which is adding it. Okay, and we are getting the output. Okay. So yes, this is very simple. Like we all know that again 1 by 81 we can't store it in. It doesn't have exact binary representation with finite bits, right? So it will be stored in its approximate form, right? So here 1 by 81, okay? 1 by 81 we are repeatedly adding 729 times we are adding to B which is initially 0, okay? B is initially 0 and 1 by 81 we are repeatedly adding 729 times we are adding, right? So what will we expect the output? We will expect 729 by 81, right? Which is 9, right? If 1 by 81 would have been stored exactly, we would have got 9, right? But 1 by 81 won't be stored exactly. It will be represented as some other number which can be stored exactly in float, right? So that number will be added 729 times. Okay. That number, if you add 729 times, that is what will be stored in the B, right? And then B will print that number. We are printing that number. So first we are doing the same thing with float, and then we are doing it with double, right? So yes, float we have only 23 bits for fraction, and double we have 52 bits, right? So as you can see, float here in the sixth decimal point itself, we are getting difference. Float is less accurate representation. When we use more bits, we get more accurate representation. We are able to represent more numbers, so more closer numbers we can find, right? So in the float, when we print only 7 digits, I am printing here. Here itself, we can see the difference. We are getting 9.00023. We are not getting exactly 9. The same thing when I do double. Here we are not writing anything. No qualifier means it is double. For float, we have written the qualifier F. Okay. So here again the same thing I am doing. I am adding 729 times. I am adding it to B1. Okay. So here as you can see the difference comes only in the 15th digit. Okay. The double is has double times precision than the floating numbers. Okay. We are getting this number which is commented here 9.0023 and 8.996. Both won't print 9. This will also not print 9. This will also not print 9. If you not write this qualifier 15 till 15 digits, if I am not printing, we will get 9 because printf will show only 5 to 6 decimal digits, and when we approximate this 5 to 6 decimal digits, we will actually get 9. So actually when we do like this floating point numbers, the errors will actually get accumulated. Okay, that may or may not be shown by printf. You may miss it sometimes, but errors are being added up. So we have to take care while writing programs. We have to consider this properly. Okay. Why do we never use double or float for representing currency? Okay. Someone from you answer this question. Why do we not use double or float to represent currency? Currency, if you are making a simulation for currency, we won't use double or float anytime. Why do we do that? We need big numbers, but we won't use double or float. We need small numbers. You want store in decimal and want to store exactly as it is and not in float or double. Yes, yes, that's correct. Yes, yes. In money and currency, generally we humans we have adapted decimal system. We are using 1 pice, right? Okay, we are using fractions of tens, right? And fractions of tens we can't represent exactly in binary, right? So we won't be able to represent exactly in the floating point numbers, floating point or double numbers. 0.1 we can't represent it in floating point number. 0.3 we can't represent it in floating point number, right? 0.2 we can't represent. So the fractions of tens we can't represent exactly in decimal numbers, and in money case we need exact numbers, right? So representing it in floating point or double numbers will cause problems. So we won't represent them in floating point or double numbers. Okay. We will use longer and we will use the last decimal digits. Like we'll multiply it with 100 and we'll use long. Those type of things we'll do. We won't use float or double. Okay. Last question we have. Here I have an code. Okay, so you have to tell me how many times will A get printed. What is the output of this code? Printing all numbers from 0 to 6. No, it's like a loop. Okay. Run this, it will run an infinite loop and it will break your system. Okay. So don't run this program. Yes. So here we have A is short, unsigned short. Okay. So unsigned short, what was the maximum number we saw here, right? Unsigned short, the maximum number is 65535. That is 2 power 16 minus 1, right? So this number 65536, that is greater than 65535. Okay. So A is unsigned short, we have 65532, and in each iteration we will be doing A plus plus, right? So after it has reached 65535, okay, it will go back to 0. The number, if you add 1 again to the unsigned short, it will again go back to 0 and it will start from there again. And again when it reaches 65535, again when added 1, A will become 0. Okay, and so on, it will be repeating in a loop again and again. So this will be an infinite loop. Okay, it won't stop at 65535. Okay.
Why it was happening?
Why was?
It was happening means.
What
Can you
was?
show that again? Means why it was in loop? Means, can you show it again?
Okay. Okay. See, here we have 65536, right? And A we are initializing with 65532. Okay. So first it will print 65532. Then A plus plus, it will become 65533. It will print that. Then 34, it will print that. 35, it will print that. Then after 35, okay, after 35, when we are incrementing it, it will become 0. Okay, that is how C++ numbers work. Okay, after the range is reached, it will again start from beginning. Okay, so A will become 0. So when A becomes 0, 0 is again less than 65536, the condition is met. Yeah. So generally we write loops like this, right? A less than n. Yeah. But we have to take care here. We have to see the limits and we have to write accordingly. Here although 65535 correctly, 65535 is one where we are also expecting it to stop, right? When 65536 we are writing, we are expecting it to stop at 65535. But when A is incremented, it doesn't become the next number. So it becomes 0. So when it becomes 0, the condition is again true. And so it will again print from there 0, 1, 2, 3 to start printing. Okay. Did you get it, Naman? Hello. Am I audible?
Yeah, I got it now. I got it now.
Okay. Okay. So that was what I had. So now if you guys have any doubt, you can ask. Anything from these topics, roofline model or floating point number. If you have any doubts, you can ask. I will upload the slides also, so you can see that also, and if you find anything, like if you can't understand anything or you have any doubt, you can ask.
Hi, Gaurav.
Yes. Hello.
So are we done with the session?
Yes. Yes. Teaching part is completed. Yes. Like
Okay. Anything else
presenting.
is pending?
No, nothing is pending from my side. If anyone has doubts, they can ask.
Okay. Okay. Thank you. So attendees, if you have any questions, please ask him through the chat box, or if he'll be available for a couple of minutes. Okay. Otherwise, you also have his email ID. Did you post him? Did you paste it actually? The email ID?
Uh, my personal email ID. Yes, I
Uh-huh.
will share. I will
Yeah.
share.
Please share it on the chat box
Yes.
so that in case they have any issues, they can contact you directly.
Yes.
Thank you, Gaurav, for your time in giving a live session. I think we are done for the today. Let's meet tomorrow. The first lecture will be by Professor
Vishwesh,
Rich.
doubt
Yes, tell
sharing
me.
is there, no? Like 4 o'clock.
Oh, yeah. I forgot about that. Sorry, thank you.
Sparsh
So,
said
yes,
others will come. Yeah.
correct. I forgot it. So, we have a doubt clearing session also, 4 o'clock. So, till then, you can take some break.
Yes, I have
You
shared
can,
my email ID. So if anyone has any query or any doubt, you can mail me also.
thanks, Gaurav.